To truly understand how revolutionary AI-designed rocket engines are, it is necessary to look at how propulsion research has traditionally progressed over the last 70 years. From the V-2 rocket to the Saturn V, from early Soviet engines to modern reusable boosters, nearly every breakthrough followed the same pattern: trial, failure, redesign, and incremental improvement. Each new generation learned from the scars of the previous one. Engineers memorized failure modes, combustion instability, injector burn-through, turbopump cavitation, and built psychological barriers around them. These barriers protected lives and budgets, but they also silently narrowed the space of acceptable designs. Innovation became cautious by necessity, and caution gradually turned into habit. Artificial intelligence does not inherit those habits. When an AI-driven engineering system is asked to design a rocket engine, it does not know which configurations are considered unsafe by tradition unless those risks are encoded mathematically. It does not fear instability, it calculates it. It does not avoid thin walls because they seem dangerous, it evaluates stress margins precisely. This difference fundamentally changes how design space is explored. Where human teams often avoid entire regions of possibility because they appear risky, AI explores them systematically, rejecting only what violates explicit constraints. This is why AI-generated engines often appear to violate intuition while still remaining fully compliant with physical laws. One real and measurable advantage of this approach is the optimization of injector design. In traditional engines, injector plates are often designed using established patterns that promote stable combustion, even if they are not perfectly efficient. AI systems, however, can simulate fuel oxidizer mixing at extremely high resolution, discovering injector geometries that improve combustion efficiency while maintaining stability. These geometries may involve unconventional hole distributions, varying angles, or asymmetric patterns that would be extremely difficult to conceptualize manually. The result is more complete combustion, higher specific impulse, and reduced thermal hotspots, outcomes that directly improve engine performance without increasing complexity at the system level. Another area where AI-driven design is producing real-world gains is structural optimization. Rocket engines must be strong enough to survive immense forces, yet light enough to avoid wasting payload capacity. Human designers typically apply conservative safety factors, adding material to ensure reliability. AI systems can distribute material more intelligently, thickening walls only where stresses actually demand it and thinning them elsewhere. This results in structures that resemble natural forms, branching, ribbed, and locally reinforced, rather than uniform mechanical shells. These shapes are not artistic, they are the mathematical solution to stress distribution under extreme conditions. The convergence of AI design and additive manufacturing is what makes these advances practical rather than theoretical. Many AI-generated geometries would be impossible to produce using traditional machining techniques. Internal channels that twist and intersect in 3 dimensions, variable wall thicknesses, and integrated support structures cannot be drilled or milled conventionally. Metal 3D printing removes these limitations, allowing engines to be produced as monolithic components with internal features fully enclosed. This not only enables complex designs but also reduces failure points by eliminating welds and joints, which are often the weakest parts of high-pressure systems. Real testing data has shown that such monolithic, AI-optimized engines can exhibit improved reliability precisely because of this structural continuity. Without weld seams or bolted interfaces, stress concentrations are reduced, and thermal expansion occurs more uniformly. These are subtle advantages, but in rocket propulsion, subtle advantages compound quickly. A small increase in reliability can enable higher operating pressures, which in turn improves efficiency, which then allows for greater payload capacity or reduced fuel mass. The cascading effect of optimization is one reason AI-driven design is so attractive to propulsion engineers. There is also an economic dimension that cannot be ignored. Traditional engine development programs often cost hundreds of millions of dollars and span many years. AI-assisted design dramatically shortens the early stages of development by automating exploration and optimization. While testing and validation remain expensive, the reduction in failed prototypes and redesign cycles can significantly lower overall program costs. This shift has profound implications for access to space. Lower costs make new missions feasible, from small satellite launches to experimental deep space probes that would previously have been financially unjustifiable. Despite these advantages, skepticism remains healthy and necessary. Aerospace engineering has always been a discipline where caution saves lives. Engineers rightly demand transparency, traceability, and validation. AI systems must therefore be treated not as oracles, but as powerful tools whose outputs require rigorous scrutiny. This is why the most successful implementations of AI-driven design are collaborative. Engineers analyze AI-generated solutions, stress test them conceptually, and deliberately attempt to break them in simulation and experiment. This adversarial process strengthens the final design rather than weakening it. The cultural shift required to adopt this approach should not be underestimated. For many engineers, identity is tied to the act of designing, to drawing, calculating, and iterating by hand or through traditional software. Accepting a design that emerged from a non-human process can feel like surrendering authorship. Yet history suggests that such transitions are inevitable. Engineers once resisted computer-aided design, just as mathematicians once resisted calculators. In each case, the tools did not diminish expertise, they changed how expertise was expressed. From a broader perspective, AI-designed rocket engines are part of a larger transformation in how humanity interacts with complex systems. We are entering an era where understanding may no longer precede creation. Instead, creation may reveal new forms of understanding after the fact. Engineers may study AI-generated engines not to learn how to design them manually, but to uncover new physical insights embedded within their geometry. In this sense, AI becomes not just a designer, but a teacher, revealing solutions hidden within equations that humans have known for decades but never fully explored. Looking ahead, it is realistic to expect that AI-driven design will expand beyond individual components to entire propulsion systems. Combustion chambers, nozzles, turbopumps, and feed lines could all be co-optimized simultaneously rather than treated as separate subsystems. This holistic optimization could yield propulsion architectures that look radically different from today's engines, yet perform better by every measurable metric. Such systems may challenge certification frameworks and engineering norms, but history shows that norms evolve in response to demonstrated success. In the end, the statement that this rocket engine wasn't designed by humans is not an accusation or a warning. It is a description of a new collaborative reality. Humans are still the ones who decide where to go, why to go, and what risks are acceptable. AI helps determine how to get there more efficiently than ever before. The flame erupting from that engine test stand was not a symbol of human obsolescence, but of human adaptability, the willingness to embrace tools that expand our reach rather than confine it. And as humanity prepares for more ambitious missions, to the moon, to Mars, and beyond, the engines that carry us may increasingly bear the fingerprints of non-human intelligence. Not because humans failed, but because they succeeded in building systems capable of exploring possibility at a scale no single mind ever could. That is the quiet truth behind this engine, and it is why this moment deserves to be remembered as the beginning of a new chapter in the history of spaceflight.